When I go hiking, especially in a new place, I will carry a map and a compass. The map is what I will use all the time, especially in a new place. I put it in a Ziploc bag, a gallon bag sometimes. This is a smaller one, so I don't see as much, unfortunately. And I just store my compass right in there with it. And as I hike along, I will keep moving my finger as I go. And if I'm following a trail, it's really easy. And that way I generally always know right where I am on the map, because the time to get oriented is right from the get-go, from the car, actually back at home, so you have a general idea. So maps I use all the time. I only pull the compass out occasionally, but I do pull it out. So let's take a look at all of the parts of a compass. The main feature of the compass is the needle. It points to magnetic north. So we'll have to have a discussion on the difference between what we call true north, almost the same as grid north, true north versus magnetic north. And we'll pause and take a look at the difference between those two. So let's take a look at why we have two norths on our maps, or even more. So let's start with just drawing a globe, the Earth, and it's spinning on an axis. So up here is the North Pole and the South Pole. And then we artificially divide it like this, like an orange. So these are lines of longitude. Then we also have the equator, and then lines of latitude across that. These are just artificial systems so that we can use it as a grid and talk about it. And this, the spinning point, and we draw all of our lines going to that, no matter where you are around the globe. Our maps, the USGS maps, the edge of the map itself points to north. The paper might be cut rectangular, but the map cuts north, and that's why those are the only lines that you totally truly trust to be true north lines. And yeah, maps of Alaska are radically tapered at the top. Back down here, even in Utah, you barely even notice that the lines are tapered. Now, so where does that give us trouble? Because if we draw, some idea of the world, here's the United States, Alaska over here. Canada's got a bunch of islands. Greenland is over here. South America coming down, and eventually we get over here to Europe and to Africa. So our maps are drawn here, but the molten core isn't spinning exactly the same as the crust out here on the surface. And it's semi-molten, and it's shifting a little bit differently. It works like a bar magnet. It has what we call a North Pole and a South Pole, which is why we call them that. But it is centered somewhere over here in the islands of Canada. So if we're over here in Utah, sorry for the exaggeration, there is the true north line that we're lined up on, but magnetic north is over here, and that gap right now for Big Cottonwood, Salt Lake, is 11 degrees. By the time you get down into southern Utah, it's a little bit different. You get up here into Alaska, and it's into the 20s degrees, and you get too close, and it stops being a useful measure magnetic north. And in fact, you get close to it and your needle just dives down and it won't rotate and spin. So you do have a zone where you can't work with it. But here we go. There is the true north line for Utah that the edge of the state is drawn on. And magnetic north, though, is a little bit different. 11 degrees for us, and that's the variance. So sometimes you'll see it represented as variance. Pilots and sailors refer to it as variance, and they use charts, where we call charts maps. when we're on the ground, and we're more likely to call it declination. How far does it decline from true north? And if you're over here, you get over here to Maine, it actually declines in the other direction, so it declines to the west. So that's why at the bottom of our maps it's going to say whatever the degrees are west, actually east, sorry for us. Maine, it's west. And the Mississippi, I haven't drawn this perfectly, is roughly in the center where, how nice, both zeros, both norths are pointing the same. So there are three main ways to deal with declination in the practical world. We're going to do the one where we compensate at the map. You can also compensate or deal with it at the compass. There are some compasses like this one that has a little bit of a screw. Let's see if I can find it. Hard to see. There we go. And a little screwdriver that comes with it. And I can turn that screw and change the alignment so that the top of Red Fred in the shed no longer points to the 0. So for here I have to subtract 11 degrees. So that's one way. And the other way is to do it mathematically. And every time you take a bearing out here on the map or in the field, depending on whether you're going from the field to the map or the map to the field, you either add or subtract 11 degrees. So you can do it at the map, which I'm teaching. You can do it mathematically, adding and subtracting, or you can do it with a compass that is adjustable. We are going to go very simply and use the map by drawing magnetic north lines. And then we will always be reporting magnetic numbers. So you have to be sure, whoever you're working with, if they're accustomed to working in true north numbers, one of you is going to have to make a change, because these numbers will always be magnetic north numbers. They'll point to the right place, but they'll be 11 degrees apart. So the needle, it's floating. You want to hold this thing just as flat as possible, and it points to magnetic north. Main feature, if that's all you had, you can do a tremendous amount with just knowing magnetic north. But there are lots of other really cool features on this compass. So it has a dial around the outside. So if we have just the needle, we know north, and therefore we know south. And we also know from that west and east. And then we can know north by northwest, or south by southwest. Or we could just break this thing down into 360 degree dial. Okay, so that's what's done. The increment marks on here are every other degree. So the space in between is the missing degree. So we have a dial. The dial spins. It has numbers written around the outside. Has a couple of other features. Lined up to the north, or the 0 point, is some system of aligning the needle. This has two. One, it has this, looks like a shed tipped on its edge right there. And it also has, harder to see, but they glow at night, 2 lines and dots. So different compasses have ovals. Most of them have some kind of an outline that then you try to put the magnetic needle inside. So that often gets called Red Fred, the needle, and then that's his shed. So there are times when we will turn it until those two are lined up together. Okay, and you'll see that parallel to that shed are what are called orienting lines, and we'll give you some uses for those. So they turn when you turn the dial. Okay, so they're part of the core of the whole dial. Dial spins has your increments around the outside, has orienting lines. So first feature, magnetic needle. It's the part that's the function on its own. When it's flat, it points to magnetic north, as long as there isn't anything around it to distract it. So anything that is steel or iron can draw the needle out of the way. Spiral notebooks are the worst. So you'll see that when I move that clip, it distracts the needle. I take it away, it goes back, I bring it in close. So watch out, steel pens, pencils. I also check the rocks by looking at my needle and watching it as I lower it and see if it gets distracted when I bring it down close to the rocks. So that's our needle. Dial with its numbers. And then the last part is this base plate. There, it looks easier to see against the tree. So it's a rectangular. Some companies keep it rectangular. This one obviously has curved it so it fits your hand better. So when I hold it, it fits in my hand. And then I have straight edges. These edges are parallel to the center. This is called the direction of travel. This compass doesn't have a line right at the direction of travel. It instead has two red ones, one out on each side, and then they're also parallel, the sides of the base plate. All of those point the same direction. So we have a needle, a magnetic north pointing needle. We have a dial with its numbers and its orienting lines, and then we have a base plate with a direction of travel arrow or arrows, and then parallel sides. So those are the three main parts of the compass. So a compass by itself, it shouldn't be that scary. It really only does one thing, and that is point to magnetic north. Once you have an understanding of the maps and all of its symbols, its colors, its shapes, its angles, and a compass, we can do some interesting things by combining the two of them. Sure, I use the map all the time, and I pull the compass out just occasionally, but what the compass does in combination with the map is it allows us to orient the map, and orient means to align it perfectly to the terrain, so that's a definition you need. And then it allows us to take bearing angles off of an oriented map and apply them to the real terrain, because of course the terrain is by definition oriented to itself. And then the last thing we can do is we can take bearings out of the terrain and apply them back to the map, because we might be able to see an awful lot on the map. We can always see a lot on the map. We can't always see it when we're down in the terrain. Sitting up here today, yeah, we're at a high spot that's somewhat like a map view, so we do get to look around. But once you're down in those trees, like right here in front of me, you can't see much of anything, and it would be nice to have a compass angle to help keep you on track in the direction you're going, and even enough to check on a trail to make sure you're on a trail that's going in the right way.